thank you, Giovanni, for this invitation to be part of this seminar. And also, it's a nice transition from Damien's talk, and I also wish Damien a speedy recovery. So I will talk a little bit about several results that we have recently published in the framework of a European project named NEURONN, which is on energy efficient neuromorphic computing based on oscillatory neural networks. So this works. I will talk a little bit about the underlying devices and the materials, but this work is very much focused and motivated from the need of AI at the edge. So what we are seeing so far that a lot of deployed machine learning algorithms are trained on the cloud or data centers or in HPCs, but at the edge, there is mainly inference that is going on. So on CPUs, GPUs, or on FPGAs, but there is currently a need to be able to have this capability to process and learn some of this incoming data at the edge. So given that there will be billions of these devices in the coming years, it's important that there is also this capability of how to train them. So this learning into on this type of devices. And why this is important, because now, as there are so many, there will be so many of these deployed devices, there is an issue with respect to the bandwidth. So inference per second. So what would be also the latency? So how many images per second can be treated? And also there is privacy concern. Sometimes this data cannot be sent to the cloud. But more important that we are also trying to address in this work is the power consumption, so the energy efficiency. So how to be able to perform some of this, not only inference, but also learning on the edge, while have limiting resources and also a limiting power consumption. In the same time, this has to be a design that is also scalable, that can be deployed in a low-cost manner. So we saw this as an opportunity in this project to be able to look into a novel computing paradigm based on oscillatory neural network as an energy efficient hardware. So we're looking at this from the materials, devices, and all the way to the circuits and architecture. And again, this is into brain-inspired computing, so going beyond the NEUMANN architecture and from the main challenge of the memory bandwidth and the memory bottleneck between the separation of the memory and CPU units. So the idea here is to go into an architecture that is fully computational memory in order to be able to address this challenge, but also to allow to perform many more complex functions, which are very much what's needed into these deployable devices at the edge. So to go a little bit more in depth to our topic here in terms of oscillatory neural network, we are very much inspired from biological neural networks, especially the rhythmic behavior and the spike and fire. And this is very much into ubiquitous in neurocortex, but also in hippocampus and olfactory bulb. And also this is from neuroscience, there's an understanding also that this is also some of the memory formation based on the synchronization of the various different brain waves. So from EEG signals, this is the type of signals that you will be able to monitor. And the idea here is to use this type of signal synchronization as a method for computing. So to give you a little bit of an understanding, an intuitive understanding to this. So for example, from a digital logic point of view, when we design circuits, we encode information 1 and 0 with respect to the voltage amplitude, such as a VDD will be the logic 1 and ground will be the logic 0. So here the idea now is to encode information on the face of this type of signals. So for example, signals that are completely in phase, there will be a logic 0, and when they are out of phase, for example, 180 degree, that would correspond to a logic 1 type of information. So the idea here is to be able to encode information on the face, on the different between the signals. So this is an alternative in terms of computing, and you will see the reasons why we are going to these phase-based computing for low power consumption. So again, to kind of illustrate this concept, you can think of metronomes. So you can think of them as starting at random time, and they are, for example, using the same sort of coupling board that allows them to adapt while they are where they are actually ticking, so back and forth. And after a while, you'll see that they're all locked in frequency. You might have seen this type of experiments with metronomes, and it can be a fun physics experiment in the classroom. And what is interesting that they are all stabilized and they lock in frequency. As I mentioned earlier, what is important is to use this type of physical phenomena, so the natural way of computing based on oscillators, but to perform low power computation. Because now, as you can imagine here, we are less important or less interested into the voltage amplitude of the signals, but more interested in the phase dynamics of the signals. So this allows us to really reduce the voltage amplitude and allows to be able to encode even more information on the phase difference between them to allow low power computing. So now the challenge is, how can we go to implement this really on hardware? So what would be the basic elements and also the material properties to facilitate this kind of computing paradigm? Again, this is another a little bit an illustration, but to start to perform with phase-based computation, we are not starting completely from scratch. We are very much inspired by the Hopeful neural networks, and back in the 80s, where they perform they perform associative memory type of tasks. So the way that the coupling, which is also the memory of this system, where the coupling is, the coupling weights are determined, is also the memory in terms of what is memorized or the patterns that have been memorized on the network. So for example, you can introduce a fuzzy image, which each pixel would represent an oscillator. And after several cycles, the correct output can be obtained. So this is, in a sense, the very much typical Hopeful neural network, but now applied, adapted with oscillatory neural networks. But there is more to associative memory that ONNs can perform. And I'll show some examples throughout this talk. So again, coming to the neuron, the idea is what would be the underlying devices and the architecture to implement oscillatory neural network in hardware. And we went through this on various ways. So the one is to be able to look into novel materials. So for example, we looked into a transition metal decalganide, so molybdenum disulfide, as a synaptic array for performing the weights, so the synaptic coupling between the oscillators, and the main oscillator device will be based on a phase change material, so vanadium dioxide, in order to be able to have this hysteresis behavior to also perform this oscillatory behavior that we require for this type of networks. And again, to kind of give you a little bit of an understanding to what is the difference of the oscillatory neural network versus, for example, other like spiking neural networks. So in spiking neural networks, we are very much interested into the fire rate, so also into the amplitude of the signals, when do they spike, and this is the type, for example, of information that you need to process. While in oscillatory neural network, we are more looking into as I mentioned, into the phase difference between signals to be able to encode, for example, a logic 1 and logic 0. So this is the main difference in terms of how we compute from a phase-based computing toward, for example, a spike-based computing neural networks. So with that said, I would like to take you a little bit into the materials and devices, the work that we have carried on throughout this time, but also some of the challenges that remains. So for the oscillator, so for the main device, which is a phase change metallic to insulate, so insulating to metallic type of a device, so based on vanadium dioxide, we have worked on two types of devices: the planar device, so vanadium dioxide with nickel and gold contacts, and more scale devices to order to be able also to sharpen a little bit the hysteresis of these type of devices as crossbar. So these are the type of devices that we're currently working, so with platinum type of contact. So in order to be able to also shrink the geometry, but also this contact area. The idea here is to have a sharper type of control and also sharper hysteresis on this type of devices. So what is of interest for a vanadium dioxide devices that go through this insulating, so they're from monoclinic type of phase change, also to go with the rise in temperature to metallic, so rutile type of phase. So this insulator to metallic transition happens around 340 Kelvin. And we have this type of behavior, which is mainly this phase change, mainly due to Joule heating, but it can also be triggered by applying, for example, a bias such as current or voltage. And the idea is through this hysteresis behavior to utilize it to create, as you'll see in a little bit, the oscillatory device for the oscillatory neural network. And here we've done a lot of quantum mechanical type of simulations, so DFT-based simulations to understand, for example, what is the interface between the device and the metal contacts. And we, for example, performed here with gold and also with platinum in order to also understand this thermal interface resistance, because it's also a signature of these type of devices. And it's also important to see, for example, what would be a suitable, not only device geometry, but also the metal contacts that we can further improve the device performance. So what has been interested here for this type of device, for example, we saw that with platinum, the distance it's much closer. So it has a stronger chemical bonding versus to gold. And we have also started to look into the various defects with the VO2 and the impact as well on this thermal resistance between the VO2 and metal contacts. Similarly, we have looked into the between the MOS2 and metal contacts. So for here we have the type of device that we are currently building in the clean room have a molybdenum bottom electrode, so MOS2, and top electrode is gold. So we looked into the studies to understand the contribution of the both electrodes, and we found out that with molybdenum there is a strong chemical bonding versus van der Waals type of gap between gold and MOS2. And interestingly, also, we try to, this is some current work that we have just published, is to also understand the various type of growth methods for MOS2, and also the defects impact into the charge transfer, but also into the interface with the electrode. So we have looked into, for example, the sulfur, disulfur, molybdenum, and also the interface, the different type of defects on the MOS2. And what we have learned so far, so this is to kind of give you a little bit of and you can find out more about this work also in the recent published work. What we have found is that the sulfur vacancies are quite detrimental for the quality of the contact. And also what we are seeing is that anti-side molybdenum atoms and grain boundaries really improve the quality of the contact. So depending on the type of growth, this is also something that we are also experimenting. So CVD or PVD based, you'll see that the different growth methods also have an impact into this between MOS2 and the electrode, the interface, which also will change later the charge transfer and ultimately the memristive effect, which we're also trying to understand. And this is some of the ongoing work which we're currently carrying out for the MOS2 devices. So with this, a little bit of an overview on the materials. Now let me go into the devices. So what type of performance and what type of behavior they have in order to be able to compute with phase-based computing. So for this, we are using TCAD, so technology computer aid design type of platform, where we have the self-consistent type of equations, so Poisson equation, continuity, and current equation, in order to be able to understand, for example, for these type of devices via diff diffusion, to be able to have as closely a physical-based model from the experimental data for these devices. So here, for example, this is for the TCAD calibration for the VO2 device. And here we are able to, from the experimental data, we can calibrate the RT, so the resistance versus temperature, and also the resistivity versus temperature. So the model that we, in order to be able to capture the IV signature of this type of VO2 devices. So the most important part is the threshold. So when do the voltage, so insulated to metallic transition occurs, and also when the voltage from metal to insulating. So these points, in order to also know how to bias these such devices to be able to get the oscillatory behavior. So that to kind of give you an idea how we can have oscillations based on these devices, you would need an external resistance and capacitance. And in order to be able to bias it in this negative difference resistance on the NDR region, to be able to obtain this oscillatory behavior. And the amplitude of these oscillations is very much based to the IMT and MIT points. So from these devices, we can further now build circuit level, which also my expertise are very much on the circuit design and also on the computing. So how to use these models, which are based on the physics based models from TCAD, but driven from experimental data into performing some computation. So the very first one is, what can we do with a single oscillator? So a single oscillator, the most important part, as I mentioned, is to determine what would be the external resistance and capacitance in order to be able to bias it correctly into this NDR region so we can obtain oscillation. We have also now have an analytical method to represent the dynamics of an oscillator based on VO2 and also coupled oscillators. And we are able to even to do, for example, some simple image detection type of application. So as you can see here, these are 9 coupled oscillators, and we have an extra one to be able to perform edge detection applications. So you can see fully coupled type of a network, and it is trained via Hebbian learning rules, so unsupervised local learning rules, to be able to detect, for example, a vertical bar or a horizontal or a diagonal as this. And using this little network to scan an image versus state-of-the-art, for example, Sobel or Uncanny algorithm, we can perform and we can obtain, for example, the edges from this original image. So just to show you the associative memory, so be able to train this oscillatory neural network based on this, again, these are based on the VO2 type of physical models to perform such applications which other type of machine learning algorithms can perform. The other thing we did, and we have currently, this is currently on arXiv, is to understand, okay, what is the energy efficiency and the of this type of system, and how does it compare versus the state of the art? And we very much looked into state of the art and what has been published from Intel in terms of benchmarking delay and energy for example, for neuromorphic chips, which are here in blue, and also for the digital neural oscillators here in red. And also, how do we compare, so the ONN with respect to also what we expect with scaling, the device scaling, with respect to neuron delay and also neuron energy. And here we had to make some assumption in terms of VDD and also the parasitics, because this is, again, based on some modeling. This is not a full chip, while the neuromorphic and the neural oscillators are real chips. So from the ones, for example, you can see here, there are various chips that you can also find open source, and then you can try to be able to compare with them. And these are more some of the, for example, from industries such as True North or Loili. So what we are, and ONN, it's here, and also this is the current state where we are in terms of neuron delay and energy. And with scaling, which is currently what we are working on the clean room to be able to scale, so the crossbar devices, to be able to scale. So we see this sort of a trend. Again, what is missing from this comparison is the overall a chip in order to be, so this is only at ONN, but the ONN, the neural network would also have some peripheral circuitry, which is currently missing from this estimation. But just to show that this is an optimistic comparison, but also the potential of the oscillatory neural network to be able to perform some, for example, tasks such as what would be needed on the edge type of devices. Again, it's a very first level comparison, but it's also an encouraging to continue further develop this technology. So in parallel to the materials and devices you just saw, we are also performing other proof of concepts for the oscillatory neural network. So currently we have a tape out, an ASIC ONN, which is a small scale, but to show the proof of concept, so CMOS-based ONN on 65 nanometer technology. But we also have been able to have a printed circuit board type of implementation of this oscillatory neural network. So these are analog oscillators, so based on discrete components, and this is the matrix to be able to have the coupling between them. And we have been able to show, for example, to perform some optimization problems, such as max cut or graph coloring. And I would also encourage you to look into the YouTube channel of our project NEURONN to have some of this understanding of how we actually implemented. So there are some short videos to show you some of these experiments running in our bench. What we've also been able to do is to implement as an algorithm the phase computing on an actual edge, for example, on an actual device such as this robot here, and to be able to perform, for example, proximity sensor measurement and to issue a command into the motors to be able to do obstacle avoidance. Again, here is the algorithm, the ONN. It's not the actual hardware, but it's the algorithm, the ONN, that is actually utilized to perform this real-time computation. And so, as I mentioned, we also have a digital version. So we have the novel materials and devices based ONN, the CMOS analog ONN, but we also have another version of it, which is the digital on ONN on FPGA, to be able to also perform, for example, some real-time applications, for example, streaming image on a camera. And for example, here we are able to perform image some image treatment. So there is an image coming from a camera that which being processed from ONN, and you can see a real time the reconstruction of these images. The other one we have done, we started with a small, for example, robot with 3 sensors, and then into an 8 sensors to be able to do this real-time obstacle avoidance. Again, this is to take this paradigm of phase-based computing to explore and what can we do with it, what would be, for example, the benefits and the costs of this type of computing paradigm. And more recently, as I mentioned as well, we have done it for edge detection type of application. So this is ongoing work, and this is a little bit different from the scope of this work, but I just thought to mention that there are also the application and benchmarking that we are trying to also push further to understand all the advantages of this computing scheme. And I would like to say that this work is done in collaborative, not only at the NEURONN level, but also in my team with various experts, postdocs, and also PhD students carrying out this work, and also to the NEURONN project partners, which they are highlighted here. So with that, I don't want to go over time, but I hope that I gave you a glimpse what it means to compute on face-on-base, and also the materials, the devices, and also the architecture that we are currently developing. So with that, I would like to thank you for your attention.